Hi everybody, I'm here in my basement and I've got my special little metal collection here, and I've picked out two of these cubes. They both say that they're 10 ounces. This is 10 ounces of iron, 10 ounces of copper. As you notice, maybe they have a slightly different volume because of their density, and you're experts on that. But I'm going to ask you this. Which one of these cubes, since they both weigh 10 ounces, which one has more atoms? Or do they have the same number of atoms? That one has more atoms. Even though they weigh the same mass, they have different numbers of atoms. If we just go to our friend the periodic table, we can see that iron is 55.85 AMUs, and copper is 63.55 AMUs. So since an atom of copper weighs more, there are less atoms in this cube than this cube. That's the kind of thing we need to do sometimes. We need to talk both in terms of things we can weigh. I can weigh both of these and see that they're 10 grams. But what formulas are atom ratios. And so we need to switch back and forth between mass and atoms. And so that's what we're going to talk about today. Let's go to work. Well, hey everybody, hey, Mike here. And as you see, we're going to talk about some ratios today in terms of, we'll start with a question. Actually, it's a provocative question to start with. Someone says to you, water. What percent hydrogen and oxygen is water? And you'd have to say, well, I need to know how you want that answered. Do you want it answered in terms of the ratio of atoms, being it's H2O? I could say it's 66.6% hydrogen and 33.3% oxygen. If you just let me, you're probably wondering where'd the other 0.1 go, but I try to simplify these things. So you could say by atom ratio, water is 2/3 hydrogen and 1/3 oxygen. How about by mass? Well, we do this kind of stuff very often. We try to prove that formulas have what we call definite proportions. That if you take water and you break it down, which by the way is no small feat. If you were to break it down, you could say, and then weigh the components of it, you could say that, well, there's 2 times the hydrogen, and that is 2 times in the periodic table. We can look up the number of AMUs of hydrogen, 1.01, and that would be equal to 2.02 AMUs. Fair enough. I could do the same thing with oxygen. That would be 1 times an oxygen from the formula. It's 1 times 16 AMUs, 16 AMUs. So in total, water is going to be 18.02 AMUs. And if we were to just find the percentage, we could say, all right, percent hydrogen by mass is 2.02 AMUs divided by 18.02 AMUs. And so the contribution of water's mass by hydrogen is pretty darn small compared to the ratio. By the way, I forgot to say multiply by 100%, right? It would be 11.2% hydrogen. And then, trusting that I didn't goof up there, I could then say then it must be 88.8% oxygen. So which way is right? The answer is yes, both are right. They're just different representations. Let's try another compound. How about good old blood sugar? I just raised mine by eating a sandwich. So we're going to find out what the percent of carbon, hydrogen, and oxygen is. Of course, if you look at it by atom ratio, it looks like it's half hydrogen. But if we take the carbon, we got 6, sorry I made my C a little weird there, 6 times what a carbon is to the periodic table, 6 times 12.01 AMUs. And that's the contribution of carbon, so 6 carbons, I should say, in that formula. C6H12O6 is blood sugar, glucose, 72.06 AMUs, carbon. And let's go do the same thing. I like hydrogens because they're easy to deal with. They're always $1.01 a piece, 1.01 AMUs. And you know all why that is, because there's some heavier isotopes, but not much of them, but that's 12.12 AMUs. Hydrogen. Oxygen, 6 times what an oxygen is, it'd be 6 times 16 AMUs. And so that would be 32. And then, I always get nervous that I'm going to do it in my head and then goof something up. So that's 96 AMUs. So a glucose as a whole weighs 96 plus 12.12 plus 72.06 is 180.18 AMUs. And to find the percent of each, we would divide the portion that is each element divided by the whole mass. We would call this, well, let's talk about what that is called. This is called the formula weight. You heard atomic weight. It's called other things, which I'll talk about later. I don't want to use a term that we're not at yet. So that's the whole thing. So I want to do percent carbon. According to the formula, by atom ratio, carbon is only 25% of glucose, but by mass, it would be the 72.06 AMUs divided by the whole thing times 100%, which in this case would be 72.06 divided by 180.18 is 39.99%. Carbon. See, so those are different representations of the same thing in different ways. Yeah, it's 25% atom ratio or atom percentage because there's 6 atoms out of 24. But in terms of mass, it's quite a bit different. It's more. By mass, by atoms, hydrogen is half of a glucose, but hardly even close to that when we take the mass ratio, which would be the amount hydrogen divided by 180.18 AMUs for the whole thing. And it's a very, very tiny, and that's because hydrogens are light. So you see, if we were to go and bust apart a glucose and capture all the elements, which can't do that perfectly because hydrogen would not come off. It'd come off as water. But if you were to take all the elements and weigh them up, they would, have much different proportions when we do it by mass, 6.73%. And then you could find the other one by just taking 100 minus it, if you didn't goof up, by the way. So if I didn't goof up, which I don't think I did, if you do it the way I did it, nope, let's do it the way I did it for the others. So percent oxygen would be 96 AMUs divided by 180. Why is this a better way? Because if I did goof up, I would find out, because you all know that all those percents have to equal 100. 96 divided by 180.18. And I was going to take the lazy way, which was to just subtract 100 from it, but I did the extra work. And the payoff of that is that 53.28%, 53.28 plus 6.73 plus 39.99, that is right on 100. And so that's an easy thing to do to determine the percentage of each element in a compound. Now, a little bit of trivia. If you're a gardener or a farmer, you see that kind of thing all the time. There's a little thing called an NPK number. That's the percentage of this particular fertilizer. Sometimes they're just pure compounds. And that's the percentage of nitrogen by mass, phosphorus, and potassium, which are very important nutrients for that. So you get these kinds of ratios all the time. If you're into gardening, you say, what's the NPK of that stuff? Oh, it's a 333. Oh, it's not as strong as an 888. That kind of thing. Folks, here's where this gets a little tricky. Let's do this problem. We're going to do a reaction. And we're going to go and take iron, which we were talking about at the beginning, and we're going to take sulfur, and we're going to react it to make a compound, which is, actually, you know the name, is called iron 2 sulfide. So we're going to take that, and we're going to do a before and after picture. And what's going to happen? Are they both going to run out at the same time, the iron and the sulfur? Well, I kind of tipped you off to that in the beginning. Turns out they're not going to run out at the same time because they have different atomic masses and there's a different number of atoms in 10 grams of iron than there is 10 grams of sulfur. So what do? Well, we have a new unit, and that's what we're here to talk about today. What we had before was AMUs. Why is that? The same reason someone said we need to have a unit called a foot so we can explain how far we are away from something. So we said, okay, you know, the protons and neutrons weigh about the same. Let's just call that an AMU, atomic mass unit. But if you were to weigh a proton, that's the mass of it, extremely, extremely tiny. So we have a new sort of, and by the way, that's also a very sort of not relatable mass because I can't weigh a proton. If we were to go take a mass of, you know, some compound, you'd take numbers of grams of it. So we have a new unit called a mole, and I want to show you where the number comes from. And I don't know where mole came from. I think it's a truncation of molecule or something like that. But if I were to multiply this by the number of particles that is in a mole, all right, so this would be times, that's called Avogadro's number, 6.02 times 10 to the 23. So we have that, and that's going to be how many particles there are in a mole. Notice I said particles. This is like dozens. It doesn't matter what kind of donuts you have, a dozen is 12. And so it's kind of like the dozens of chemistry is that number. Now look, we shouldn't even have to really use our calculator that much. 6.02 times 1.67 is 10. If you multiply these two powers of 10, they add. This would be 10 times 10 to the minus 1. That is really the same thing if we go ahead and put that power of 10 on there. That is 1 times 10 to the 0, which is the same thing as saying 1. So what is a mole? All right, a mole is 6.02 times 10 to the 23 particles. Once again, it's kind of like the dozens is to chemistry. But it's also the number of particles in a gram of protons or a gram of neutrons. So it is equal to the number of particles, protons, all right, number of protons, the number of neutrons, because remember that was what we called an AMU, in 1 gram. So a gram of protons and a gram of neutrons is going to be 1 mole, and so we call that 1 mole. And the symbol for it is MOL, because if you knock the E off, you save like 17 seconds every semester. But that is the number of particles in an AMU of a proton or a neutron. So, looking big picture, we're going to need to use moles to solve problems, and what that means is that number that you see for a mass number, let's look at something relatable like carbon. 12.01. That is how many grams of carbon is in a mole, which is 6.02 times 10 to the 23 atoms. 18.02 for water. All right, remember back to water? 18.02 AMUs. That means that if you took Avogadro's number, 6.02 times 10 to the 23 number of molecules, you'd weigh 18.02 grams. Any element on this chart, 6.02 times 10 to the 23 atoms, is the number that is its atomic mass in grams. So you see, the mole is what is sort of the bridge from grams to particles. And so now what we could do, we could solve our problem a little bit easier. I'm going to go ahead and I'm going to convert each of those two numbers to moles. Now once again, remember, you're just using your periodic table here. You're not having to memorize anything. 10.0 grams of iron. And what I'm going to do is I'm going to go ahead and say grams, 1 mole. And we go look it up. We kind of talked about it earlier, 55.85. So I'm going to take and find out how many moles that is. 10 divided by 55.85. 0.179 moles. I'm going to write that up here. So let's go put that up here. 0.179 moles. Let's do the same thing with sulfur. 10.0 grams sulfur. 32 oops, made it sound like it was a magic trick. 32.07 grams sulfur, 1 mole sulfur. 10 divided by 32.07, 0.312. So now, when we look at it in moles, see how it's much easier to see who's going to run out first? The iron's going to run out first because there's less moles of it. And by the way, this is how we write equations. There's nothing there, which means a 1, a 1, and a 1. And so formulas are all in moles. H2O means 2 moles of hydrogen for 1 mole of oxygen. Chemical reactions are written in moles. 1 mole of iron reacts with 1 mole of sulfur, makes 1 mole of iron 2 sulfide. And so moles are going to be the bridge that we always have to go through to solve problems. And so, but you know, notice in a lot of cases though, I didn't have to dwell on that big, huge, clumsy number that is Avogadro's number. And people make a big deal out of it, but you usually never need to know that number. You just need to know that that's what a mole is, and you convert it into moles, and then you find mole ratios is how we find formulas, or how we write equations that are chemical reactions. And so, you know, Avogadro's number looks intimidating, and then they make, you know, sort of fun things about it, like Mole Day is October 23rd. And personally, I think there should be Mole Moment. Mole Moment, Mole Minute is 6:02 p.m. on October 23rd. Notice I didn't make it a.m. because I don't want to get up that early. I like 6:02 p.m. better. So this year, let's go celebrate Mole Moment, Mole Minute. It's like some other things I've heard, but this is much more wholesome. 6:02 p.m. on the 23rd of October. Folks, more on this to solve more problems next time, but just remember, we didn't need to know what Avogadro's number was. We just need to know that Avogadro's number of atoms of anything here is this mass in grams. So now we have in our toolbox not just AMUs, but grams per mole. And that's where we're going to go next time. We will see you then. Toodles!